Okay, hello everyone. So we'll start off with section 5.6 in this class, and that section is called Complete Equations of Elasticity. So what we do in this section is basically we summarize everything which we have learned in this course up until now. Okay, now this does not mean that if there are parts which you have not understood will somehow be brushed under the carpet. No, I mean, if you have not understood any part until now, that part will keep on propagating until you actually understand it. So I request you to please go back and see anything which you think you are in doubt, or you are not sure, or you are not clear, and make sure that you understand it uh, before this section gets finished off. Okay, so you are free to sort of pause a video and go back and take a look before you, until you are clear of what is exactly happening. Okay, so we refer to this big word called the theory of elasticity. So this is the name given to that body of knowledge which deals with the distribution of stress and strain in an elastic body subject to given loads, displacement, and distributions of temperature. So if you have this elastic body, three-dimensional, and you have so-called mechanical loads, you have displacements, and you have a thermal loading, and you would want to find the distribution of stress and strain in this solid, meaning if this is your origin, then you should be able to point the stress vector and the strain vector at any point of this solid. So that's what this position vector x shows. This is what the theory of elasticity is. Okay, that's the one word or three-word summary of it. Now we are able to state the foundations of this theory right now, and we are in somewhat of a position to do it. There are other parts of boundaries which we will deal with later on, but we will have the relationships as such completely for ourselves. Now the problem is to find the stress and strain which meet the prescribed load and displacements on the boundary, and which at every point within satisfy the equilibrium equations, the strain stress temperature relations, and the geometrical conditions associated with the definition of strain and the concept of continuous displacement. So basically everything which we have studied all this while. So that's what we will want to do. Okay, so there are, and these are again of those three steps which we had laid in equation 2.1. Okay, equation or this collection of steps in 2.1. So we do that first, and let's see how we can write down. So first thing to note is that at all points, at each point, the point is non-accelerating, hence in equilibrium, isotropic, linear elastic. And small strain. So these are all valid for everything which we are doing below. So what was the first step of 2.1? It was equilibrium. So within the body, I mean a point which is internal to this three-dimensional body, they must satisfy the equilibrium equations. We have derived them, I think, in chapter 4. So let's see what that equation is. Where that is 4.3. Yes, 4.13 or 4.14. Please check these equations. We had made a derivation of it. We had obviously used the two-dimensional plane stress situation, but we would want to extend it to 3 dimensions. So the equilibrium equations inside the body, meaning every internal point of this 3-dimensional body, should satisfy the following 3-dimensional equilibrium equations. So we have derived them already, so we are just writing them for a 3-dimensional system. So this is equation 5.6. As you see, there are equilibrium equations, and x, y, and z, which you see, the scalars over here, they are body forces. Okay, so body forces are like the force of gravity, and they are shown in the 3 directions of x, y, and z. Okay. So that's why you have these 3 body forces over here, and you can uh, write the equilibrium equations like this. So these are essentially generalizations of the 2-dimensional equations which are given in 4.13. Okay, so 5.6 is that. Okay, so from now on, if we refer to equation 5.6, it would mean this, what is in front of you. So many a times the force of gravity or other body forces are ignored. In that case, x plus and y and z will be 0. If they are not, then you just assume them to be there. Okay. So because in the derivations, when we derived equation 4.13, we did not consider body forces. Okay. So that is just one extra term. That, and remember, this acts at one point of this solid. So at one point of this 3-dimensional solid, these equilibrium equations hold. Okay, so that's the first part of it. Let's now move ahead and write the next term, which is, let me just cut it out over here. For 2.1, the first was equilibrium, the second would be about geometric compatibility, and this is essentially the relationship between stress and strain and displacement. Sorry, okay. So this is the strain displacement relationships, and we have also derived this at some point. I think for a 2-dimensional case, we did that in equation 4.33. Let me check that. Equation 4.33. Yes, so equation 4.33, if you see, this was derived by us, or defined by us, to be more correct, for a 2-dimensional setting. And what we do here is a extension of that. So we write epsilon x as dou u by dou x, gamma xy as dou v by dou x, plus dou u by dou y, and epsilon y is equal to, so at some point I may have made an error in speaking, not writing, but speaking what gamma xy is. I mean, I may have wrongly said it as dou v by dou y, so you can just make that correction if I have. I think I have made it once, but this is the correct one. So it is dou v by dou x plus dou u by dou y. So epsilon y is equal to dou v by dou y, and gamma yz is equal to dou w by dou y plus dou v by dou z, and epsilon z is equal to dou w by dou z. Gamma zx is equal to dou u by dou z plus dou w by dou x. So this is the strain displacement relations, and these are, as I've said, three-dimensional extensions to equation 4.33. This is 5.7. So if we say what please, using equation 5.7, that would mean using the strain displacement relationship, which is the geometric compatibility in the language of steps 2.1. Okay, so after this, we would want to have like an extension to the stress strain relationship. The relationship between stress and strain. That was the third step, remember? And that we would do by, say, let's do this over here, is the stress strain and also temperature relation. This is the most general case. If you think that there are no temperature changes happening or not considerable temperature changes happening, we will just take the temperature part to be 0. Okay, so we had found the Hooke's law, the generalized Hooke's law, remember? This was 1 by E sigma x minus nu sigma y plus sigma z plus alpha of t minus t naught. So we superimpose the strains due to the mechanical loads and the thermal loads. The reason we could superimpose them because they were both small. Both the strains were small. Okay, and similarly sigma y minus nu sigma z plus sigma x plus alpha t minus t naught. Well, as we had seen in the last class, the strain in the x direction due to the thermal effects will be the same as in the y direction and z direction, because they are all normal value, only normal contributions are there and of the same value. And similarly this would be sigma z minus nu of sigma x plus sigma y plus alpha t minus t naught. Gamma xy is equal to tau xy by g. We had derived all of it. Okay, if you remember, you should be able to show a derivation if ever asked. Okay, you should be clear of the steps. And the reasoning which were included in those arguments. Okay, so this is equation 5.8. okay, so 5.8, if ever referred to, is the relationship between stress and strain, including thermal effects. So if there's no change in temperature happening, you would automatically see that this term would be 0, so the thermal strains would be 0. Okay, so the equilibrium equation 5.6, okay, the strain displacement relations equations 5.7 and the stress strain temperature relations 5.8, they provide you 15 equations for 6 components of stress, 6 components of strain, right, and 3 components of displacement. So let's verify this. So 5.6 has 3 equations. 5.7 has how many? 1, 2, 3, 4, 5, 6 equations. Okay, and 5.8 has 6 equations. So there are a total of 15 equations in these 5.6, 5.7 and 5.8. Okay, and they will help us for, I mean, 6 components of stress, 6 components of strain, and 3 components of displacement. Okay, so these 15 equations are the foundation of what we call as the theory of linear elasticity. Okay, and the equations are linear. Okay, the equations are linear because the linear material behavior assumed in 5.8, and also because of the restriction to small strains. So all of these equations are said to be linear for this reason. Okay, an additional consequence of 5.7, okay, is 5.7 is the strain displacement relation, is that the strains are associated with undeformed configuration. So if you look at this one, this is basically a small change in the displacement along the x direction. Okay, so they are associated with the undeformed configuration. So what was the initial configuration? Where was the point O initially, and now it has moved to the point O dash. Okay, so that's how these are defined. They are associated with the undeformed configuration, and this in turn means that 5.6 represents an application of equilibrium equations in the undeformed configuration. So that would mean that this equilibrium is actually applied in undeformed configuration. So at one point these equations are defined in the undeformed configuration. This in turn means that 5.6 represents an application of equilibrium requirements in the undeformed condition. Thus the complete equation 5.6, 5.7 and 5.8, I mean 5.8 very clearly because the strains have been found using these stresses, okay, which had these relationships in the undeformed configuration. So they apply, so 5.6, 5.7 and 5.8, they apply to deformations of isotropic, linearly elastic solid, which involve small strain and for which it is acceptable to apply the equilibrium requirements in the undeformed configuration. So this is very important. Perhaps we are making this claim for the first time. Okay, if it was implicit, okay, it was implicit, but this we are making it out loud for the first time, that this was actually the equations of equilibrium were applicable in the undeformed configuration. Okay, now in order to obtain solutions of these equations, remember we have these 15 equations and we would still want to find the stress, how it varies within the solid, and strain, how it varies within the solid. So for that we would have to solve these equations. So in order to obtain solutions to these equations, it is generally necessary uh, because the derivatives which appear in 5.6 and 5.7, you will have to perform integrations over that. I mean, look at these equations. Okay, so you will have to do integrations because all these partial derivatives exists everywhere, and that is where this step of integration would come in. Now as you know, every time you do an indefinite integration, I mean like you have done I think in chapter 2, chapter 1, you integrated from 0 to x, 0 to L, you have to apply certain boundary conditions. Like in some cases, the reaction forces was fixed, or the shear force at the boundary was fixed. Some cases it was zero. Okay, so that is what is called is a boundary condition to fix the solution. Okay, so that it's independent of these constants which you will have. You will need to also prescribe boundary conditions at every point on the surface of the body. So most commonly used boundary conditions are, so the idea is, in order, because of the integrations are involved, so you will have certain conditions at the boundary of this solid, okay, surface of this solid, and the solid is 3D, so that we don't leave this. Okay, there are certain boundary conditions which have to be satisfied, and there are many ways these conditions can come up. Okay, so the most common methods are displacement, okay, and displacement vector of the boundary point is specified, meaning at points of the boundary you will have displacement specified, and so on. Okay, infinity sign just to show that it is acting on the boundary. That's the one method. The other is that you would have so this would happen on the entire boundary. This is the first method. Okay, the displacement would be specified on the entire boundary. So that's how you would I mean go with it. Okay, so the second is the stress vector on boundary. So if you look at if you look at section 4.2, for example, you would find that the stress vector can be shown like this. On every point of this solid you will have this possibility. And the third is mixed, meaning part of your boundary will have displacement specified, part of your boundary will have the stress vector specified. On this note, I will also say that the stress vector is also called traction. Okay, we may not use it much, but I think you should know this, that the stress vector is also known as a traction vector. Okay, now we are making a claim about the uniqueness. So as the author of your textbook says, that it can be shown, we will not do that in this course, but it can be shown that if at every point on the surface of an elastic body, either the displacement vector or the surface stress vector is prescribed, then there exists a unique solution which satisfies 5, 6 and 7 throughout the interior, which meets the prescribed boundary conditions on the surface. So this is a very powerful idea of linear elasticity, and this is the reason why, despite like this field being say 100 or more years old, we still use linear elasticity. And I'll tell you it, repeat this part again. If you have a three-dimensional problem like this, you have a solid, you have a combination say of the displacement boundary conditions, you have the stress vector or the traction vector boundary conditions. Okay, I'll show it by Tn. Then you have only at any given point on this, you will have a stress and a strain and a displacement, and that is what you were trying to find. 6 of this, 6 of this, 3 of this. They will all be unique at this given point. They will be unique at any given interior point on this. Okay, and they will be satisfying your 5.6, 5.7 and 5.8, which is the foundations of this. So there cannot be two stresses, like there cannot be at this point, there will be only one sigma x, there will be only one gamma xy, there will be only one value of displacement u1. Okay, so all of them will be unique given your boundary conditions are fixed. So, and your linear elasticity, isotropy, small strain, all those assumptions are valid, meaning equation 5.6, 5.7, 5.8 hold on every interior point. And that's what, and they will also satisfy the boundary conditions clearly. Okay, so that's the uniqueness of linear elasticity solutions. Problem is that you have the boundary conditions defined. Solution is to be able to find the stress, strain and displacement at every point in this solid, and they will all clearly satisfy 5.6, 5.7 and 5.8, which is essentially an upgraded version of the steps given in 2.1. Okay, so just to tell you, just for your own knowledge, and as it is also given in your textbook, that even when the material is not linearly elastic, meaning even in a case when there is plasticity, when the material is plastic, okay, clearly the strains are not small, then uniqueness still holds in special cases under special conditions. Okay, so there are advanced theories which deal with all this, but for our understanding and for the case which we deal with, our solutions will always be unique. The proof of this uniqueness is beyond the scope of this course. That is why we are not studying this over here. uh, okay, so perhaps at some point later in your life, if you take up a course in elasticity or advanced solid mechanics, that is where you are expected to learn that. Okay, so that is sort of the summary of what stress strain relations are in the most in the on the complete equations are, and we have read about these things, and now we'll be applying to some of the problems to see whether we have actually understood it. Okay, so for that I will actually have to remove a lot of things, so let me do that in a slightly faster way. Okay, so we refer to example 5.2. Okay, we'll have to go, I think, all the way over here to. I'm not removing the green pen part because I don't think that's there anywhere in the book. That's just sort of coming from your knowledge of linear algebra, which all of you have by this stage. If not, you should definitely revise parts of that course which are appearing over here. Okay, so this is example 5.2. Okay, let's see that. Okay, so in this one you have a long thin plate of width B. Okay, so this is a long thin plate of width B. So L and B are shown to us, there is a thickness component of T that is shown over here. So the XY axis is this, the YZ axis is shown like this. So I think you are seeing this particular thing from this side. So this is your eye. If you see this from this side, you should be able to look at it like this. So the thickness is T, width is B, length is L. It is placed between two rigid walls of distance, a distance B apart. Okay, the distance between them is B, and they are acted on by axial force P. Okay, so you have a force along the axis, which is P, shown in the figure. We want to find the deflection of the plate parallel to the force P. Okay, so the objective is to find the deflection basically in this direction, okay, along the force P. So that's the objective, and let's see how we proceed in to solve this problem. So this is the A, which you see is the actual problem. Okay, we have discussed that with the dimensions and how these two things are coming, and then we always have an idealized model. So let's look at that idealized model. This is it. Now in the idealization, what we do is, rather than having this force which acts like this, we assume there is a stress which acts like this. So P will be divided by the area, which is B into T, same over here. Okay, and then that's the first part of it. There is no normal stress in the thin direction. Okay, so this is essentially a case of plane stress. Every time you have this thin solids, you can assume a plane stress, and then there is no normal in the thickness direction. So in the Z direction, there is no normal stress. So sigma of Z will be equal to 0, which is the case. Okay. Now then the third part about this idealization, and that's why you are not shown. I mean, you don't see a sigma Z in this figure. Okay. Now the third idealization is that there is no deformation in the Y direction. Okay. And you can see the reason why, because it is actually constrained in the Y direction. So there is no deformation in the Y direction, and that's why you don't have a deflection which is shown like delta Y like this, that is equal to 0. Okay. The last part is that the normal stress of contact between the plate and the wall is uniform. So this entire contact region which you have on the top and the bottom, that is uniform. That's an assumption, idealization which we are taking, and that value is sigma naught. Okay, so sigma naught at the top face, sigma naught at the bottom face. So this is how you draw the idealized diagram for this, which is B, and the objective is to find the this delta by 2. Okay, the deformation in the axial direction. And the difference this time is that we would be using the theory of elasticity which we have developed. And the problem of elasticity is always like this. What you see notice now is that you have the boundary conditions specified. Okay, let me show. The boundary conditions are specified. Okay, there are some other boundary conditions which are actually not included in the diagram, like the deformation in the Y direction is 0. Okay, so that is shown. So EY is equal to 0, and then these boundaries are specified. Now at any internal point on this, one should be able to find the stress. We are not going to, but one should be able to find the stress, strain, and the displacement. So it seems our work will be done if we are able to find the displacement at this point, okay, or on this edge. If this displacement is found out, then we have the answer to our problem. So that's what we are trying to do over here. Okay, let's see how that happens. Okay, first step is always the equilibrium. With the external loads is satisfied when the stresses existing in the plate are. So sigma x has to be equal to minus p by bt. Okay, and because sigma x is I mean on the from the external forces, this is p by bt, so it has to be minus p by bt. Similarly, sigma y has to be equal to sigma naught, and sigma z is equal to 0. Okay, so this is what will be happening, and the shear stresses are all 0 just because there are no external shear stresses. So this is the idea, and this is the next part is, I mean, for any x this will be there, or any x comma y, meaning any point on this will have these values. So you are assuming this uniform behavior which is reasonable for a problem like this. Okay, so that is the first part of it, which is equilibrium, and clearly they all satisfy these stresses, will satisfy 5.6. So what you must do right now is try to check whether this stress field actually satisfies equation 5.6. So what you have to do is you have to actually put these values sigma x, sigma y, sigma z and the other stress components into that equation and confirm whether that is working, whether that equilibrium equation is valid. Okay, so that's what must be done. Okay, so that's the first part of it. The second part is clearly the geometric compatibility. So I'll just write it, say, over here. Hold on. Yes, so the second part is about the geometric compatibility, and that is that because the walls are rigid, so clearly this strain in the y direction is 0, and because it's, I mean, the only important part about this is the x, okay, because it's a long thin plate. So the only important, I mean, the diameter, so strain is 0 at the boundary, and because b is small compared to L, it is 0 throughout this. Okay, and there is a reason for that. Let me tell you that reason. So you know that strain at this point and this point, so let me just draw it over here. So the strain at this point and this point is 0, so sigma y is equal to 0 and sigma y is equal to 0. Now why do I say that it must be 0 internally as well, meaning why should it be 0 over here and here and here and so on? The reason is this: if e of y, if epsilon y has to actually be non-zero, say it has to increase. So if this is your value and this is e epsilon y and this is its value, so let's assume that the value increases, but then it must come down to 0 again, right? This is fixed definitely, or it can move in any other way you would want. Okay, now this is the logic. Since b is small, b is so small, so this will not offer it enough distance for it to actually increase and then come back to 0. Hence it is reasonable for you to assume that it is, even if it increases, it will increase only a very small value and then again come back to 0. So that is why it is reasonable to make this assumption that the strain in the y direction is 0 throughout, okay, and not just at the uh, boundaries. And that's all a part of plane stress, plane strain, especially this rigid problem which you have. So in this case, it is because of the rigid walls which you have. Okay. Now, in terms of delta, you now move to the x direction. You have the epsilon x is equal to minus of delta by L. So because it's a delta by 2 on each side, the total deformation is delta and the original length was L. So the strain in x direction is like this. You have a negative sign because clearly it's a compression. Okay, so the third step is the relationship between stress and strain. And since nothing is given about the temperature, so you would assume that the temperature throughout is constant. So you have to now use the Hooke's law. So you can write Ex is equal to 1 by E sigma x minus nu sigma y. Okay. Similarly, you can write the other components. And once you solve all this equilibrium, geometric compatibility, and the stress-strain relationship, you would be able to find that sigma y is equal to nu sigma x is equal to minus nu p by bt, and delta would be equal to 1 minus nu square pl by e bt. Okay, and then you would have the strain in the z direction as nu by 1 minus nu delta L. So please verify this. Don't take it at face value. That way we can also check whether what the author has done in his textbook is correct, in their textbook is correct. Please derive this and confirm. So these expressions are given in your book as equation E. Okay, and that's where you note the that is, and the next part would be about the strain displacement relation. So let's write the strain displacement relation. You see that we keep on sort of playing with the order in which we apply the steps, but overall all of it has to be done, and until all of it will be done we will not be able to solve the problem. Okay, so the strain displacement relations is what we would be discussing right now. So for this, if we consider the origin of the coordinates to be in the center of the plate over here, okay, this is the center of the plate, and assume that this, and also it's not just center on the surface, you see it's also on the center of this thickness. So the origin is in the bulk, it's an internal point that you can see over here and over here as well. Okay. And this point will not move either in the x or in the z direction. Okay, the origin will not move either in the x direction or the z direction. Can you think of a reason why it is fine for us to do it? Fine for us to assume that the origin does not move either in the x direction or z direction. Okay, so any guesses? I mean, why this can be done? So first of all, in the x direction, it is reasonable to say that clearly there is a symmetry in the loading. Okay, so whether you extend it or compress it, it will not really, the center point of this will not move because of the symmetry. If it was some other point, then yes, there would be some movement, but the center point of it will not move because of the symmetry, and for the very same reasons it would not move in the z direction as well. Okay, so this origin will not move over there either in the x or the z. Now then we substitute the strains into equation 5.7. Okay, so the strains which we have calculated uh, in equation E, okay, above, you put that in 5.7, which is the strain displacement relation, and then you integrate all 6 relations. You will get U is equal to minus delta L by X, and V is equal to 0, and W is equal to minus nu by 1 minus nu delta L by Z. So the displacements very clearly depend on your X, okay, and the strain was not actually depending on X. That is implicit in this fact. If you see Ex, it would be dou U by dou X, and it would be minus delta by L. Okay, the reason we had to do this because this strains had to eventually conform with the boundary conditions also. So that is how this has all played along. So please actually see and derive this. Please do not leave it for guesswork or something which you can just look at and see. You cannot, very likely you will not be able to mentally just integrate this and find all these values and physically understand the problem. So please don't hesitate doing all these derivations. And you have got the displacements now inside the plate. So V clearly will be 0 because you did not assume any strain in the Y direction. So V will always be 0. U clearly is minus delta L by X, and there is displacement in the X direction over here. Okay. So we have obtained a rigorous and exact solution to the elasticity problem. You have found out the stress, strain and displacements inside this long thin plate, okay, given the boundary conditions which you had. So you have solved this elasticity problem. This is your first elasticity problem which you have solved. So you should all give a pat on your backs. And again, if there's a doubt, you will have to go through the derivations again. It is very important at this point to not overlook this method which we have taken, because if there's a doubt in this, there will be doubt in the rest of this course. So please don't let it pop anywhere. Okay, so one of the things which you should note, that you didn't actually solve this problem or A. What you have actually solved is B. Okay, if you had solved A, you would have said you have solved the exact problem. What you have solved is actually an approximate problem. Okay, and there is a difference between these two things. I mean, you have clearly seen. So there is a concentrated force over here. You have taken a stress. Okay, now the problem of 5.17a was itself an approximation to a more realistic loading over a small region of contact. Okay, so on the basis of experiments in similar situations, it is probable that the overall deflection of the actual plate is near that estimated from the idealized model. So though you have solved an approximate problem, it is expected that the displacements which you are getting would be very close if you had to do this experiment in which you would apply a concentrated force like this. Okay, so because this concentrated force will actually, in theory, it applies to a point, but it acts on this very small region. Okay, because the with whatever you are trying to apply this force, it will develop a contact region, and this will have this uh, force which is acting over a small area. So this is a way how you would solve a problem approximately, and it is found out that these methods by and large work. So one of the other things is that the solution of this method is actually very good if you are away from the boundaries, meaning if you are, say, in a region like this, which is away from all the boundaries, then this answer which you have calculated is actually much more accurate. Say compared to the displacement of this point, okay, say the displacement at this point, the displacement somewhere over here internally will better match the experiments rather than the displacements over here. Okay, so this is something to do with the boundary effects, which you don't have to worry again. But the point is to say that these methods work well if you want to find the solutions which are in the bulk. So this difference in the boundary does not play much role if you are in the bulk away from the boundary. The difference in these between the actual and the approximation and the idealization. This is called Saint Venant's principle, and we will read it in slightly more detail in the next section. Okay. The idea is that, I mean, the basic idea is that if you have something which is very complicated at the boundary, okay, and you don't really know how to solve that, so you can take something simpler. Of course, I mean, the total force has to still be P. So you can take an assumption like this, in which P by 2 acts and P by 2 acts. Okay. Or P by 3 acts in 3 parts. You can keep on doing that. Okay. And doing that, as long as the forces are statically equivalent at the boundary, the loading is statically equivalent, the solution inside the bulk of the solid, solution meaning the stress, strain and the displacement inside the bulk, will be approximately the same as it would be in this complicated boundary condition case. So this is Saint Venant's principle, and maybe it will pass through it once more in the next chapter. This is again an important part of linear elasticity theory. Okay, so we'll stop over here and continue from the next section in the next class. Thank you.